Thanks for joining us for another episode of DPC Radio. This episode was recorded live in Amsterdam at the Dutch PHP Conference 2012. For more information about the Dutch PHP Conference, visit our website, phpconference.nl.
Please put your hands together for Mr. Douglas Crockford.
Good morning. I have two distinct topics for you this morning. The first one is programming style. Programming style is a part of a program which the compiler ignores. And since the compiler doesn't pay any attention to it, there's a school of thought that says we don't have to pay attention to it either, that one programming style is as good as another. I'm going to try to convince you today that that's not the case, that some programming styles are significantly better than others, and I'll show you why. The other topic is the brain. The brain, you remember, is that big wad of meat that lives in our skulls that we sometimes use to think with. Now, you would think these two things, programming styles and brains, would have absolutely nothing in common, nothing to do with each other. But there's actually a connection, a surprising connection, an important connection. So I'm going to be misrepresenting the work of Daniel Kahneman. Kahneman is a Nobel-winning psychologist. Now, Nobel does not give a prize for psychology, so they gave him the prize for economics. He doesn't do economics. He's a psychologist. But he found some really interesting stuff, which invalidated one of the first principles of economics, which is that in any transaction, a party can be expected to try to pursue its own best interest. And Kahneman shows this is not necessarily the case if one of those parties is a human being. That we don't think, at least the way economists think we think. And generally, we don't think the way we think either. So Kahneman came up with a model with two systems. System 2, which could be called the head, is methodical, it's rational, it's algorithmic, it's where we do mathematics and logic. It's capable of amazing deep thinking, but it is slow and requires a lot of effort in order to do that kind of thought. Then there's System 1, which could be called the gut, which is associative, which is heuristical, is very fast, cannot be turned off. It's automatic. It's on all the time. And it will substitute a simple solution for a hard solution, often without our being aware of it. The thing that Kahneman found, which is so surprising, is the connection between these two. I mean, we've always had this sense that my head tells me this, but my gut tells me that, so that the idea that they're two systems isn't new. The thing that is new is the relationship between them. It turns out that the gut provides the working set for the head. And the gut is often wrong because it's doing approximate stuff. It doesn't understand arithmetic at all. And the head is unaware that its premises are being given to it by a fallible system. And as you know, if you have a logical system and you give it false inputs, you can get false outputs. And it turns out we do this all the time, and we're not aware of it. The more you study Kahneman, the more amazed you are that we ever get anything done, because the way we get things wrong is fantastic. So let me show you an example of this from visual processing. Visual processing is the opposite of computer graphics. It's where you take a signal from a camera and analyze all of the pixels and try to determine from them all of the objects that are in the scene and how they are moving relative to each other and the camera. This turns out to be a really hard problem. And with massive supercomputers, it's still a very difficult thing to do well. We do it all the time automatically without even thinking about it. And it's obvious that there's huge evolutionary value in order to do that. That, you're being chased through the jungle by a cybercat. You need to very quickly solve the problem to find a way between the trees so you don't run into something or trip. And we do it in real time, and we're really good at it. But in order to do that with this big wad of meat that we think with, we are constantly taking hard problems and replacing them with much easier problems. But a consequence of that is sometimes we'll get wrong answers. So This is an optical illusion that was developed by Edward Adelson at MIT. It shows a checkerboard or a chessboard with white squares and black squares, and there's a cylinder on the board that's casting a shadow. You might be surprised when I tell you that square A and square B are exactly the same color. You put them in Photoshop and you put the dipper on them, they have exactly the same pixel value. Now you may be struggling with that and say, no, one's obviously black and the other's obviously white. They can't be the same color. So I took a solid colored square and connected them. Okay, and you can see there's no break. Now some of you may be seeing a gradient. That's because there's another system in your brain which is looking for inconsistencies. And when it finds an inconsistency, it will change its understanding of the world in order to make the inconsistency go away. And that turns out to be important because, you know, in a computer system, when we get inconsistencies, that usually leads to failure, right? And you can't have that in a living system. So instead, we adapt to this. If you're seeing a gradient, take your hand and cover up square B, okay? And you will see the gradient disappears. It turns into a solid gray box. And then if you drop it, the gradient comes back. Okay, you know the truth of this picture. Your brain is lying to you. Knowing the truth, you cannot force yourself to see this correctly. Now, there's some people who can see this correctly. We call them artists. And they're able to do this either because of some defect or training. They are able to see the world as it actually is. And they can communicate that back to the rest of us through their art. It's an amazing thing. That's why we should praise art. It's a great thing. Now, it turns out this doesn't happen just in our visual system. It happens everywhere. All of our thinking systems are subject to this kind of stuff, where our brain is replacing hard problems with simple problems, which sometimes produce incorrect results, and we make assumptions based on those incorrect results. We do it all the time. Now, it turns out this was not news to the advertising industry. They've been doing this stuff for decades, maybe centuries. They know that there's a way that they can create a message and deliver it straight to the gut and convince us that we want something that we absolutely don't need. They've been doing this for a long time. And nobody is better at this than the tobacco industry. I mean, you think about selling tobacco. What does tobacco do? Okay. It makes you smell bad. It turns your teeth yellow. It makes you sick, and then it kills you. Okay. How do you sell a product like that? How do you convince people, yeah, I want to do that? You don't sell to the head, right? You're selling to the gut. You're using imagery and messages which confuse the gut. For example, the gut is very much attuned to short-term danger. But long-term danger is kind of indistinguishable from good for you. And so we'll make very bad decisions. Now, that is the same brain. The brain that can be tricked into buying tobacco is the same brain that we use to write computer programs. Computer programs are the most complicated things that humans make. You know, you look at a program, you look at all of the operators and symbols that are involved in it and how they're combined, and the way it also has a temporal component, maybe a multidimensional temporal component. It's really complicated. There's nothing else that humans make that is as complicated. And there's nothing in our evolutionary background to prepare us for doing this. It's sort of a miracle that we can write computer programs. Now, early on, it was recognized programs are just too hard to make. So we should figure out a way to have the computers write the programs for us. And so work began in artificial intelligence. AI has produced some amazing results. For example, it can play chess really well now, can play a pretty good game of Jeopardy, but it still can't write programs. You can't give a set of requirements and a set of user interviews to a program and say, write a program. We can't do that. If we could, what would have happened was we would ask a program, write a program that's better than you. And it would do that. And then we'd ask it again and again and again until they became our overlords. But that hasn't happened. That aspect of AI has been a complete failure. We don't know how to do it. So we're still writing programs the old-fashioned way, by hand. It's still a craftwork thing. We've tried to automate parts of it, and the more we can automate, the more effective we are at doing it. The most important tool we have is the programming language. It leverages the ability of computers to translate one formal language into another. They can't write the original program, but given a program, they can turn it into another program. And that turns out to be a useful thing because it allows us to raise the level of abstraction. And every generation or so, we'll lift it up a notch. And so that improves our ability to be able to write programs. The thing that makes programming so hard is that it requires perfection. And we are not good at perfection. I in particular, am a deeply imperfect human being. Perfection is hard for us. But the contract we have with the computer is that the program must be perfect in every aspect for all possible inputs, for all possible states. And if it is not, if it is flawed in the slightest way, the computer has license to do the worst possible thing at the worst possible time. And it's not even the computer's fault. Whose fault is it? It's your fault. You're the ones who get the call, the program doesn't work, something's wrong. How could you have done that to us? So, you would think that recognizing that, we would hold on to programs and not release them until they're perfect. The thing is, we know so little about perfection with relation to programming that we wouldn't recognize perfection if we saw it. We have no way of knowing. We know that it passes its test sets, but that's not proof that it's perfect. And in fact, everything that ever went out in the field that passed its tests and then failed is sort of evidence that the tests do not even approach perfection. So we're programming with the brains of hunters and gatherers. We are hunters and gatherers. There's been no human evolution since the hunter and gatherer era. And there's nothing in that experience to have selected us for computer programming. So it's amazing that we're able to do it. And I think it's because of we're taking advantage of all of the tools that we have available to us. So programming obviously uses the head because so much of it is analytical. We're keeping all of this state and all of this logic in our heads and manipulating it. But I think the gut is there too, because one of the reasons why we can't teach the computers to write programs is that we don't know how we do it ourselves. In the process of transforming a set of requirements into something that can execute and do them, we don't know how we do it. We can't write down the steps and give it to someone else and say, this is how you write a program. First you analyze the stuff, then you go top down and do this. No, then we go bottom up, and then we go inside out, and then we large view, macro view, micro view. We're constantly switching back and forth, changing our perspective on the thing until we finally get it working. And we can't describe how we do that. There's something magical going on. And so that tells me that the gut is involved in that there's something in the way that it works which gives us those flashes of insight which make the whole thing possible. If it were not for the gut, we would not be able to write programs. I have absolutely no evidence to support that statement. But my gut tells me it's true, so I believe it. So programming is all about making trade-offs, right? It's almost never the case that there's always exactly one way to do it. The dilemma is there are many ways to do it, but at any moment you don't know which is the one which leads to perfection, even if there is one. That's just unknowable. And some of the choices we make have consequences, either in performance or in size or in robustness or other things. And so we need to make trade-offs. But the difficulty is that much of the trading off happens at the gut. And the gut is not logical, it is not mathematical, and so it often gets stuff wrong. Speaking of getting stuff wrong, I'm going to be showing you some examples in JavaScript. JavaScript has surprisingly become one of the world's most important programming languages. It is famous for having good parts. In fact, it has some of the best parts ever put into a programming language. Those parts have since become very popular, and you now find them in lots of other languages. but JavaScript was the first mainstream language to do this stuff. It also contains bad stuff, bad parts, probably more bad parts than any other programming language, as a consequence of it being designed and implemented in 10 days, which is an insanely short amount of time to develop and implement a programming language. So all languages have good parts and bad parts. JavaScripts are better and worse than any other language. No other language has that breadth going from the ridiculous to the sublime as JavaScript. But all languages have bad parts. But I'm going to be illustrating this stuff in JavaScript. Many of the things I'm going to show you that are wrong in JavaScript are wrong in C, are wrong in PHP, and lots of other languages. So when I'm writing in JavaScript, because of the huge bad part set, I was sort of afraid to program in it because you can go wrong in so many ways, and it's difficult and expensive to discover the ways that it goes wrong. So I wrote a program called JSLint, which reads my JavaScript programs and tells me when I'm using the bad parts. And it turns out it's surprisingly easy to use the bad parts. So it defines a professional subset of the language, and that makes my programs more reliable, more maintainable, all of those things that we want our programs to be. So if you're writing JavaScript, and if you're not using JSLint, there's something wrong with you and your code. Now, JavaScript comes with this, or JSLint comes with this warning. JSLint will hurt your feelings. And it's true. And I hear from people all the time writing me, JSLint hurt my feelings. Wow, can you make it stop? And after a few years of that, I started to wonder, what's wrong with us? It's a code quality tool. And the reason you'd run your code through JSLint is because you want it to tell you how to make your code better, because we're trying to attain perfection, and perfection is really, really hard to get to. And anything which moves us in that direction for free should be considered a good thing. And people start to cry when they're using JSLint. And he goes, but you asked it to tell you that, so what's going on there? There's something deep and strange happening there. So let me give you an example. So when Ken Thompson designed B, which became the inspiration for C and virtually every other language since then, it was the first curly brace language. Actually, there was actually BCPL before that, but let's say B was the first one. And there's a question, where do you put the curly braces? Thompson and Ritchie and a lot of other people said, well, let's put them on the right. Not a good reason to say on the right or the left. There really is not a good reason to prefer one or the other. And right away, there are other people in their lab who said, no, we want to put them on the left. And I'm sure they had a meeting. And after a couple of weeks of meeting discussing which side the curly braces go on, Thompson and Ritchie said, we don't care. This is a stupid argument because there's not a good reason to prefer one or the other. You just have to pick one. It's sort of like driving. There's not a good reason to drive on the left or on the right, but there's a really good reason for us all being on the same side. People in England think the left is obviously the right side, and the rest of us would say, no, the right's the right side. And you can look at driving patterns on both places, and people seem to drive as well. There's no empirical evidence which prefers one side or the other. It's just a good thing there's not a road between here and England, so it's not an issue. So there are some things you can get people to agree on. You should be consistent. Because if you sometimes put them on the left and sometimes put them on the right, it looks stupid. Or trying to be perfect, and you don't want to be looking stupid when you're trying to pretend to be perfect. So that's counterproductive. You don't want to be confusing people who are reading your program by trying to figure out why is he doing that. But somehow we have this emotional attachment to it. So if someone who's used to putting them on the left goes to work for a shop that puts them on the right, and he's told, here, we put them on the right, he'll start to cry. Go, what? I don't want to put them on the right. And start coming up for reasons for why he should want to put them on the left. And the reasons don't make any sense because it's not a good reason to put them one way or the other. But something in his gut is telling him, this is important. I wouldn't be crying if I wasn't right about this. And he'll start to get kind of hysterical. So I think in retrospect, Thompson did the world a huge disservice by not saying, put them on the right, damn it, or you get a compilation error. And that would have ended the thing, and we all go, okay, we'd all put them on the right. Instead, who knows how many man-centuries we've wasted since then arguing, do they go on the right? It's just punctuation. What difference does it make? It's just, this isn't something that should make us cry. So it turns out in JavaScript, there's a right answer. In JavaScript, alone among all languages, there's actually a case for where you want to put them on the right and not on the left. If you're returning the value of an object literal, which is a very popular in JavaScript, it's the way you return a new object. If you put the curly brace on the right, it does the right thing. And if you put the curly brace on the left, it returns the undefined value, and you get no other warning in this example, which is like the worst possible thing, because it means your program doesn't fail at the site of the error. It's going to fail at some undetected or unexpected place in the future. And debugging that turns out to be really, really hard. And if you finally trace it back to this statement, you'll stare at that and go, return this object. Where did the object go? And it's because there's a stupid design blunder in JavaScript called automatic semicolon insertion, which causes this statement to go wrong. Now, if it turns out that you always put the curly braces on the right, you will never experience this failure. That turns out to be a good thing. If you put the curly braces on the left, it is likely, or at least possible, that you're going to encounter this, and you're going to waste a huge amount of time on it. So what's the difference in cost? Looking at this as a trade-off now, of putting the curly braces on the left or on the right. The cost is zero, right? It's just zero. What's the benefit? Never encountering this problem. That's a good trade-off. Since most of what the art of programming is making good trade-offs, we should recognize this is a smart way to do it. So in general, I don't know where you put the curly braces, but in JavaScript, you definitely want to put them on the right. So we want to prefer forms that are error resistant. If there are two ways of writing things and one is less likely to cause us problems, we should prefer to use the form that has less problems. JavaScript and virtually every other language since B has a switch statement. When Thompson designed his switch statement, he modeled after the Fortran computed goto statement. Now, since then, goto has been considered harmful and has been removed from most of our languages, but it still exists in the switch statement. One day, someone wrote me and said, JSLint should check for fall through, which was one of the consequences of this goto-ness in the switch statement, that you can have one case fall through into another case. And he said, this is sometimes a source of error, and you could warn for that. And I thought about it, and I wrote him back, and I said, well, there's this really elegant thing that can happen when you get all the cases to cascade and they fall one into another. And that elegance is really, it's beautiful. It's great. It's profound. It's why we program. And yeah, I could see how it could happen accidentally, but that hardly ever happens. So I think in terms of making a responsible trade-off, I think I'm not going to warn on that because the benefit outweighs the penalty. Next day, the same guy wrote to me and said, I found a bug in JSLint. I said, okay, good. I threw it in the debugger. You know where this is going, right? I had a switch statement that was falling through. In that moment, I achieved enlightenment. Because it turns out we're making mistakes all the time. And we struggle with them, we debug them, eventually we find it and we fix it. And there's this little rush of euphoria that comes with it. And then we black it out and we completely forget about it. So when we look back on what we do, we imagine we're power typing. I'm typing in a program, that's what I'm going to do. I'm saying keystrokes and all that. And we spend most of our time gazing into the void, saying, my God, what have I done? And struggling with that. So most people, when they're in that situation, will say, I'm changing majors. This is terrible. There's no way I can do this. This is just so frustrating and painful. What's wrong with you people? But in this case, it was so humiliating because I had just given this speech about how this was a good pattern and not a source of error, and in fact, it wasn't. And so I could not ignore the failure this time. I had to learn from my mistake, which is an extremely valuable thing which we do much too rarely. So what was the error in my logic, if you could call it logic? I said, that hardly ever happens, which is the way the gut says it happens. Because the gut's really bad at quantifying stuff. It's really bad at arithmetic. It thinks that most should be given more weight than all. It's just really bad at math. And it thinks a rare event is the same as a never event. And that's not the case, particularly if you're trying to achieve perfection over something which happens millions or billions of times as we cycle through our stuff. You can't think about it that way. You've got to be much, much more rigorous. And I wasn't being rigorous on that day. So I learned that a good style can help produce better programs. Style should not be about personal preference or self-expression. It's not about being an artist on the page. It's about trying to be clear about what's happening in order to express it in as perfect a way as possible. So let's talk about literary style as an analogy here. The Romans wrote Latin all in uppercase with no word breaks or punctuation. And it worked for them. They had the biggest civilization on the world for a time. And this worked until Constantine established Christianity as the official religion of the Roman Empire. At that point, it became necessary to make copies of all the religious texts and distribute them all over the world. Now, the problem was they didn't have originals of any of the texts. All they had were copies of translations of translations of copies of copies of copies. And it turned out none of the copies agreed with each other. That every time a copy was made, they mutated. Errors were injected. And this is particularly a problem when you're trying to establish an organization who derives its power from the word and nobody is sure exactly what the word is. So medieval copyists introduced lowercase, word breaks, and punctuation. And these innovations helped reduce the error rate. They also made the texts easier to read, which was a nice fallout, but not the principal intention. So when Gutenberg started printing, he copied these conventions, and we're still using today. They work. We have many, many centuries of experience with these conventions of the use of punctuation, the use of paragraphs and those forms, and they work. And so if you're a writer, you want to be using these forms because they're proven. So good use of style can help reduce the occurrence of errors. And they also make the text easier to read. There are lots of good style manuals. This is a really good one for English, The Elements of Style by William Strunk. It was published over 100 years ago. English has continued to evolve since then, so some of his advice is dated, but much of his advice is still really, really good about how to take words and put them together in powerful ways. So programs need to communicate with people the same way that writing does. Now, there's a view that the only entity that needs to understand what a program does is the compiler. And that's not true, particularly as we're getting more agile. And as our teams get bigger, the likelihood that someone else needs to understand this program too is constantly increasing. And so that the program is able to be understood is at least as important now as what it does. So we should be using the elements of good composition where applicable. There are lots of things from literary style that can map directly into programming style. So in literary style, you put a space before or after a comma, not before. So I would recommend deviating from that only if you have solid evidence that you were improving, that you're not doing this just to be wacky. You know, if you're a great author, you demonstrate your skill as an author by the things that you write about and the words you select in order to describe it, not by how you use the punctuation. You don't say, I'm an awesome writer because I put my periods at the beginning of the sentences, not at the end of the sentences. People would think, no, you're just illiterate. You're stupid. You're in the wrong field. You shouldn't be writing. So a writer will slavishly conform to the rules of style just so that stuff becomes invisible, that the reader is unaware of that, so they can focus on what's really important. And I think exactly the same is true for programming languages. But programming requires much more precision than writing does. So we need additional rules. For example, parentheses are ambiguous in our languages because we use them for syntactic forms and for grouping and for invocation and function definition. So we can use spaces in order to disambiguate those various forms. So we want to be sure to write our functions to not look like statements, to write our statements to not look like functions. Now you could say, well, the reader should be able to figure this out, but we don't want the reader to have to figure it out. It should be clear to the reader what our intention is so that they can focus on more important things. One of the nice things we can do in JavaScript is the immediately invocable function expression. It's where we take a function and execute it immediately after it's defined. Now, it turns out, because JavaScript was designed in 10 days, this is actually a syntax error. Because if you have a function in the statement position, it can't be invoked immediately. It should have been, but it's not. So it was discovered that you could get around that by wrapping the function in parentheses. But I think this misses an opportunity here because I don't want to just be tricking the compiler. I want to be making it easier for the reader to recognize what's going on here. Also, I think it's kind of weird looking that those extra parens at the end that are doing the invoking are hanging out there like a couple of dog balls. The ladies may want to look away here. So my advice would be to move everything inside of the parens, because what I want the parens to tell the reader is this whole thing should be looked at as a unit. That this is the important thing here is the invocation. It's not just the function by itself. It's the fact that we are immediately invoking this function. That's what's important here. And if we're expecting this to return a value, the thing that's returning the value is the whole thing, not just the function. Now, I told you earlier about automatic semicolon insertion in JavaScript. This is another place where it gets you. If you have a statement, in some places, JavaScript will insert a semicolon for you. This is one of the places where it doesn't, and then there are many others. So this completely changes the meaning of this statement. So instead of assigning y to x and then invoking this function, it treats y as a function, passing it the result of the other function, which is not what anybody would ever intend, but that's what it does if you leave the semicolon out. So the most reliable way to write this is to always put the semicolons in, to never leave them out. JavaScript's semicolon insertion mechanism is it goes compiling along, and the compiler gets an error, and it looks to see if there's a line feed nearby, and if there is, it turns the line feed into a semicolon and then tries again. That should freak you out. That's like, no way, that's insane, that's crazy. It would have been nice had JavaScript been designed with a grammar that was robust enough to not need semicolons. That would have been great. But it didn't do that. Instead, it put it in an error recovery mechanism, which is itself erroneous. And if you read the ECMAScript standard, it gives you examples of where semicolon insertion fails. And a wise programmer would look at that and go, okay, I guess I won't be using that. Another thing that's wrong in JavaScript is the with statement. Here we have a with, and we have 4 statements that with statement could have expanded into. Can anybody guess which of those 4 statements is the equivalent? Anybody? Well, it's a trick question. It could be any of them. There's no way you can tell from reading the program which of these it's going to expand into. And in fact, every time the statement executes, it could be a different one. You could put it in a loop, and it's possible that every time through the loop, you get a different one. So my advice is, don't use it, because we're trying to be perfect. And if you can't read the program and understand what it does, how can you have any confidence that the program is perfect? So write the thing that it expands into instead. It turns out in this case it's actually smaller. But even if it's not, do it. Also, it has terrible performance aspects in addition to its terrible reliability problems. Now, there are clever uses for it, and there are very clever people out there who have found clever uses. They say, well, I should still be using it because it's very clever. You know, usefulness is not high enough of a bar to cross. Because I'm not saying it isn't useful. I'm saying there's never a case where it isn't confusing. And we don't want to be putting confusion into our programs. Confusion is the enemy. Confusion must be avoided. Confusion is when we think the program does one thing and it actually does another thing. That's where errors come from. So we want our programs to be clear and as free of confusion as possible, because if it's free of confusion, it's more likely to be free of bugs. This is something JavaScript has in common with PHP. We have a double equal operator which does type coercion, and so it can produce false positives, which turns out to be a terrible thing. Fortunately, JavaScript has triple equal, which does the right thing, will produce false for all of these comparisons, which is what you want. You know, these results for double equal look random. They're not. They're actually a very long list of rules which describe what it's supposed to do, but it's more than most people can keep in their heads. So my advice is always use triple equal, never use double equal. Well, you might ask, well, I've found a case where double equal actually accidentally does exactly what I want here. So should I use it in that case? And my advice is no, because the reader of your program may not be aware that this is actually the one place where double equal makes sense. You know, it's more likely that they might think that you're incompetent. So you don't want them thinking that when they're reading your program. So always write triple equal. If there's a feature of the language that is sometimes problematic, and if it can be replaced by another feature that's more reliable, then always use the more reliable feature. This is something that was added in the 5th edition, multi-line string literals. I think this was a mistake. I don't like these for two reasons. One is indentation is really important to understanding our programs. Because we have so many nested functions, the indentation is a huge cue to the reader as to what belongs to what. And these require that everything go out to the margin. And so it breaks indentation, makes programs harder to read. But worse than that, there's this reliability problem where, well, here, there's an example. There are two statements. They look the same. One is correct and the other has a syntax error. Can anybody spot the syntax error? Yeah. There's a space right there. It's obvious once it's pointed out, right? But I want people to read my program and have a sense, yeah, this is correct. So I don't want to be using forms that are impossible to distinguish from common errors. So avoid forms that are difficult to distinguish from common errors. You know, and sometimes people say, well, that was intentional. I'm intentionally writing code that looks wrong or confusing or stupid because I'm expressing myself and I'm showing people who I am. You know, I know what I'm doing. And my answer to that is, if you knew what you were doing, you wouldn't be doing that. This is something that was wrong in C, and it's also wrong in JavaScript. The statement in white is ambiguous. It looks like it means if A is equal to B, but it actually means assign B to A and test A for truthiness. So, you know, when you see a statement like that, you have to ask, What's it mean? Which one did he intend? Is this an error? The only thing you're certain of is that the programmer was incompetent. But besides that, it takes a lot of work to figure out what's going on here. And particularly if you need to change this, you have to wonder, am I making things worse? Am I making it better? It's hard to know. Now you're wasting time. That's not good. So make your programs look like what they do. This was a case where the program looked like it was doing one thing, but it was actually doing something else. Scope is one of the greatest inventions in the history of programming languages. We first saw it on Algol 60. Most languages have block scope. JavaScript doesn't. JavaScript has function scope. Now, it turns out you can write good programs in function scope, so that's enough to be a good programming language. The problem for JavaScript is that it is using the syntax of a block-scoped language. So people who come to JavaScript from other languages get confused. They think it works one way, it actually works another way. So they can make mistakes in writing, they can make mistakes in reading. And it's due to the way that the var statement works. It does this crazy thing called hoisting, so that no matter where you create a variable in a function, the definition actually gets hoisted up to the top of the function. And that can change the meaning of a program. It can cause something which looks correct to actually be wrong. So my advice is to declare all of your variables at the top of the function, because that's where they're going to get declared anyway. Make your program look like what it's going to do. There's a similar hoisting thing that happens with functions. So I recommend declare all your functions before you call them. Because of hoisting, you don't have to, but there are weird things that can happen as a result of that if you're not aware. I get more flack for this than anything else. So I tell people, declare your variables at the top of the function, and they go, but what about the for statement? I want to write for I. And no, you don't want to do that, because it turns out that I is not scoped to the loop, it's scoped to the function, because it gets hoisted just like all of the other vars. And we've seen errors happen as a result of that confusion. And they go, but that's how you write it in Java. I say, write in the language you're writing in. Don't write in the wrong language. That is a source of confusion. A lot of these languages look alike, but they behave differently in important ways. You need to be aware of that behavior. In a future edition of JavaScript, there will probably be a let statement, which is just like the var statement, except it will respect block scope. So when that happy day comes, my advice will be stop using var, never use var again, always use let instead, because we'll avoid that confusion. Unless you still have to support IE6 or IE7 or IE8 or IE9 or IE10. And we don't know about IE11 yet. But certainly if you only have to support IE12 and up, then yeah, you'll want to use a let statement. Global variables are evil in all languages. They have reliability problems because you can get collisions where one part of a program will stomp on another. Security problems come with that as well. So you want to minimize your use of global variables as much as possible. JavaScript makes this difficult because JavaScript doesn't have any kind of linker. We'll fix that in the next edition. We'll have a module system, which should be very elegant. But in the meantime, every compilation unit gets dumped into a common global space. And so the way the compilation units communicate is they're all sharing global variables, which is extremely hazardous. So we want to minimize our use of globals as much as possible. And so I recommend writing global variables all in uppercase, because these are dangerous artifacts in our programs, and I want them to stand out. I want to make it very, very clear this is a global thing, so be careful with it. JavaScript copied Java's new syntax, but got it wrong. So if you write a function intending it to be a constructor, a maker of objects, and someone calls your constructor but forgets to put the new prefix on it, They don't get any error. They don't get any warning. What happens is instead of initializing a new object, they are clobbering global variables. Again, there's no warning. This is terrible. We fixed this in ES5 strict mode, but if you're having to work on any of those other browsers that I mentioned, you don't want to rely on that. So we have a convention, it's only a convention, that constructor functions should be named with initial caps and nothing else should be named in initial caps. That's the only chance we have of being able to read a program and find a missing new. Here's another one. A equals B equals C. It looks like we're defining A and B as local variables, but we're actually defining B as an implicit global variable, which again is not what we want. So you want to figure out which one of these you mean and write that instead. Write in a way that clearly communicates your intent. Okay, this one's a little controversial. Now, controversial doesn't mean wrong. So plus plus was added to B to do pointer arithmetic. Now, since then, we've determined that pointer arithmetic is dangerous, and you don't see it in modern languages now. The last popular language to have this operator in it, or to have pointer arithmetic in it, was C++, a language designed so bad it was named after this operator. So even though we're not using pointer arithmetic anymore, we still have this in our languages to do arithmetic, to add 1 to things. And it's like, why do we need a completely different form for adding 1 than any other value? That doesn't make sense to me. But it comes with a danger in that it encourages us to write one-liners that get really complicated and try to do too much at once. That most of the buffer overrun problems that plague operating systems and system software are due to that compulsion of trying to get too much into one statement. And I find myself, if I'm using this in my program, if it occurs anywhere in my program, I get the twitch. I start trying to optimize to get things down to one line. It's a stupid trade-off, and I cannot stop myself. So I finally had to swear off plus plus. No, I will not use it anymore ever. It's just not worth it. So I'll write plus equal 1 instead. I can control that. I can live with that. I can maintain. Some people say, oh, wait a minute, I should be able to write x plus plus because it means exactly the same thing and it's 1 character shorter and that's important somehow. Except it doesn't mean the same thing. Plus plus x means the same thing. So if I'm reading a program and I see x plus plus in a position which means x plus 1, I have to think this guy doesn't know the difference between pre-increment and post-increment. It means I have to look at every plus plus in his stupid program and try to figure out, did he get this wrong? Because it's a really easy error to make. And once made, you get an off by 1 error, but it's only off for a tiny unit of time. And so they can be really hard to debug and diagnose. So it's just not worth it. Recently I was reading some code where I saw this, x plus plus x plus plus x. And I tried to figure out, okay, how did that happen? And I'm guessing there was probably an off by 1 error, and someone said, well, okay, we'll just do it again. Or maybe it's a copy-paste error, I don't know. But if it wasn't an off by 1 error, if they'd written x plus equal 1, it would have been much easier to change to x plus equal 2. Again, there's not any good reason for having to write the one case differently than all of the other cases. So for no cost, by adopting a more rigorous style, many classes of errors can be automatically avoided. And that turns out to be a really good thing. Here's another one. This is confusing. It turns out C is executed unconditionally, even though it doesn't look like it. Another error Thompson made when he designed C was, or B, he could have made the parens around the condition optional, or he could have made the braces optional. And he chose the wrong one. And I think it's because the braces looked more like Fortran. And that mistake's been made again in all the other languages. So my advice is always put the curly braces in every time. It provably makes your program more resilient. And the argument that comes back is, but it's 2 more characters, and you have to go so hard. This is the best trade-off I'm going to show you tonight. It's so easy. It's just 2 characters and makes your programs much more resilient. And that's important because as our processes become more agile, our coding must be more resilient. Other hands are going to come and modify your program. And if you just put that little bit of structure into the code, it's much more likely that other people can come in and improve it without breaking it. So programming is the most complicated thing humans do. Computer programs must be perfect, and humans are not perfect. Designing a programming style demands discipline. It's not selecting features because they're liked or pretty or familiar. It's because they help reduce our error rate. We should be focused on trying to reduce our errors, not trying to reduce our keystrokes, because it turns out the keystrokes are not where we spend the time. We spend most of our time gazing to the abyss. And as Nietzsche said, when you gaze into the abyss gazes into you. And it's soul-destroying and painful and wastes so much time. So if we want to be more productive, we should spend less time in the abyss. We shouldn't be thinking about the power typing. We should be thinking about the lost time spent trying to get the thing to work. So the JSLint style was driven by a need to automatically detect defects. In analyzing the language, there were some forms where I could not determine automatically if it was being used correctly or not. So I consider those forms themselves defective if there was a good alternative. So I don't care if it is right in this particular instance. It's just that it's wrong often enough and that there is another approach which is less wrong. That's the way you should write it. So my approach comes down to language subsetting. All languages are too big. Language designers always will push a little bit too far and add something that maybe they shouldn't have. And once it's in, they can't take it back. Once it becomes a popular language, people will find a use for it, and they're stuck with it. It's been said only a madman would use all of C++. It's been said only a madman would use C++, but that's for another time. So they don't have the power to simplify the language, but you do. You can decide what subset of the language makes sense. You can look at what features are likely to be problematic that are going to increase your error rate rather than decrease it. You can be active in making that decision. There will be bugs. I'm not saying that this approach is going to eliminate bugs. What I am suggesting is that for no cost, you can move the odds in your favor. You can spend less time in the abyss, and that will make you much more productive. So that's it. Good style is good for your gut. Thank you, and good night.
DPC Radio is a production of iBuildings. The materials presented are copyright of the speakers. This episode is released under a Creative Commons Attribution, Non-Commercial, No Derivatives 2.0 license. iBuildings is a full-service web development company specializing in PHP development. For more information on how we can help you with your next web project, visit our site at ibuildings.com. Thanks for listening, and we hope you'll join us again for DPC Radio.